Okay, let's see. I don't know why it's focusing on you guys and not me. Okay. Well, anyway, maybe I'll. Anyway, okay, so I have a test. So I still haven't graded homework 16, but I figured you cared more about your test anyway. So that first. I didn't look at the average, but y'all did well on that. So.
Nobody found it.
Yeah.
Yeah. The one person I thought that was did it. Nina.
Okay. So
Wait,
that's
are you a SoCon?
I put on the back for people to go.
right?
But yeah, Nina Williams. I thought it's all people.
Yeah.
She
she
would know
did-
Soka and she would know math.
Right. Put it together. I love it. You got the purse too. That's perfect. Awesome. Okay, so yeah, so today we're gonna go on talking about rings. And I've got a theorem to prove. Did I ever do theorem 3.2, which is the theorem 3.2 is the how to tell something is subring. No. Yeah, I don't know. You've slept since then. Okay,
No, I think we just did definition.
we just did definitions. Okay. So we'll do theorem 3.2. And theorem 3.1 is really just defining what a Cartesian product is. And so, yes, I wasn't going to do that in class, but maybe I'll do an example with Cartesian product in a bit. So, let's see, do I have a Cartesian product on here? Well, we'll do a Cartesian product example. So, okay, so suppose that R is a ring and S is a subset of R. Such that we have these conditions. First thing, S is closed under addition. Number two, S is closed under multiplication. 3, you have the additive identity is in S. And number 4, you have additive inverses. So if A is an element of S, then this thing A plus X equals 0 R constitution in S. And so we're writing it this way because we're talking about rings in general. And so a lot of times we'll call that additive inverse negative A, right? But I think we write it this way just to kind of write it a little bit more in general because they don't always look like just negative A. I mean, it may be like a matrix or maybe, I don't know. So we have different things. So this is additive inverses. So I'll put it in parentheses. So it just has to be closed under both operations, and it has to have the additive identity and additive inverses. And then you have that S is a subring. Okay. So I'm going to give you an example and let you all have a chance to fiddle with this theorem. So basically, I'm not really proving this because, okay, so what are the things that are missing to say it's a ring? So we have the ring properties. Let's look back here. Our ring properties on this handout I gave you. So you have to have closure for addition. So that's here. Associative addition, that comes for free because S is a subset of R. So we get associativity for free. So let's just keep a list of what comes for free because S is a subset. Associativity of addition. Okay. Commutativity of addition. We're going to get for free. What else? Additive identity element, that's here. Right, so additive identity is here. That's in our, we have to show that one. We don't get that for free. Additive inverses are here. We don't get them for free. Closure for multiplication is here. And so we get associativity for multiplication and distributive property for free. So basically, we get those things for free because S is a subset of R, and then we have to check these things hold. Okay. All right. So to give you a little bit of practice, let's do this example. Is the subset S equal 0, 2, 4, 6, 8 of Z mod 10 with addition and multiplication Z mod 10? A subring of Z mod 10. So we have that. Okay. So is that subset a subring? Yeah.
If we have a subring, that also means we have a ring. Like if a subset is a ring, the subring is just saying like making it clear it's a subset.
Yes. Mm-hmm. So it would be a subset that is a ring in and of itself.
Okay. Okay.
Yeah. And so to check that it's a sub ring, so this is clearly a subset of Z mod 10, right? This is a subset. I just need to check that it has these 4 properties, and then it will be a sub ring. that will have all the ring properties as well, okay? So take a minute and work that out, okay? And then if you figure that out and you feel good about that, try to make a multiplication table of that. Well, actually, the multiplication table might help you figure out if this is true or not. And then I want to ask the question, does it have an additive or multiplicative identity? So as you're writing up your homework, I don't know if you've looked ahead at the homework that's due next week, but there are a lot of things where it's like, is this subset a subring? You know, so there are a lot of those kinds of things, and you're just going to be using this theorem over and over. And so I will say that sometimes, you know, I want you to address each point on there, but like sometimes writing it all out can be like a little tedious. So do the best you can on writing things out, but you know, I don't expect you to necessarily have every single detail on there, because like to show that it's closed under addition, what do you have to show? That every pair that I could add is going to give me something, you know what I'm saying? So it's like, you don't have to show that necessarily. You could just kind of look at it and say like, okay, well, yeah, that's going to work out. So it's going to be closed under addition, you know. And if it's not, you can say like, here's a counterexample, you know what I'm saying? So, it can be a little tricky to write up. Now, 0R is an S, that one's pretty easy. And then does it have additive inverses? Well, this only has 5 elements. So I could write down what the additive inverses are. You know, that's not so bad. So you kind of use your judgment on that. But I definitely want to make sure you address all of these 4 points in some way, right? To show that you know what you're doing. Okay, so is it a subring? What do you think? Think yeah? Is it closed under addition? Yeah, it's going to be closed under addition. Is it closed under multiplication? Yeah, it's going to be. It's kind of like the even numbers. It's sort of, you know, I always think about that. Does it have a 0 element? Yeah. And does it have additive inverses? Yeah. So we can check that. So we could say, so what's the additive inverse of 2? So -2 is equal to what? Well, I'll put it in brackets. That's equal to 8, right? Because if I say 2 plus 8, I get 10, which is 0. And I could say -4 is equal to what? Six. Yeah, six. Yeah. Yeah. And so 6 is the additive inverse of 4. And we could also say in turn that, you know, -8 is 2. So the additive inverse of 8 is 2, and the additive inverse of 6 is 4. You know, so there's our additive inverses, so they're all there. And then and it has 0 in there, right? So 0 is in there. So it's gonna be, so we'll check that. So anyway, so when you're writing that up, you want to address each one, but it's closed under addition. And you know, you'll write it all up, right? So we can write that down. Okay, and then so it is a subring. Did anyone make a multiplication table? Yeah? What did you get? What, does it seem like it has an additive identity element? What do you think? Why don't you talk in your groups, get with someone else who has a multiplication table and see what you think about that. I'll try to copy mine down here. So how do we tell if it has a multiplicative identity? What are we looking for in the table to tell? What do you think? We're right?
A one.
A one? Okay. What did you say?
At the intersection. It's like,
Okay, so does it have an additive identity or multiplicative identity? No? What's the definition of the multiplicative identity element? What does it have to do?
has to have a solution for AX equals.
Oh, you're looking for multiplicative inverses, right? But what does the identity element do? What is its role?
It does nothing.
It does nothing when you multiply it.
I think it does not have an identity. Oh, I see.
So you think that
It looks like 6.
looks like sixes? What are you seeing in the table that's making you say that?
2 times 6 gives us 2, and then 4 times 6 gives us 4. 6 times 6.
Okay. You all see that? Yeah. And the other way too, I could do 6 times 2 and 6 times 4 and 6 times 6 and 6 times 8 and it leaves it unchanged. So I have here that it does have a multiplicative identity. I can see it in the table here if I look at the row and column on 6. So it does, so the one in this S is 6 actually. So do we have any multiplicative inverses? Well, when I look for multiplicative inverses, what am I looking for in the table? That
And with the products that you 6, right?
products that give you 6. Yeah, does that make sense? We want to do products that give you that multiplicative identity. Isn't this mind blowing? This is so fun. Yeah. So I see one here, right? So 8 and 2 are multiplicative inverses of one another, right? So 8 inverse is 2. The multiplicative inverse of 8 is 2. Yeah. Huh?
Oh, I was just gonna say, you mentioned was mind blowing. There's a proof I had seen a while back that any power of 6 always ends in 6.
Mm-hmm.
And like, it's kind of a mess to prove that in modular arithmetic, like directly. But if you just prove this, that multiplying by 6 just doesn't change the last digit of any number.
Oh, that's interesting.
I hadn't thought of it like that, but like, that's so much quicker because then like, since 6 is an even number, you can just use that.
Mm-hmm.
Wow.
Yeah. It's fun when you see those connections of something, yeah, you're looking at in a different way. Yeah, cool. And then I can see that 4 is its own multiplicative inverse, right? And so on. So this one does have, so this is, if it has multiplicative inverses, and it has a unity, then it is, what kind of a thing is this? So look back at our other definitions. Is it an integral domain? So an integral domain has to have what? No zero divisors. Does it have any zero divisors? No, because 0 is our 0 here. Actually, we can see it in the multiplication table because it's, you know, so 0 is actually our 0. And we don't have any zeros outside of that row and column. So I don't have any zero divisors. So it is an integral domain. Since it has unity and it has multiplicative inverses, it is also a what? It's a field. Yeah, it's a field too. Yeah. So this is an integral domain and it's a field. It's a ring with unity, it's an integral domain, it's a field. So this is a field. All right, cool. Okay, so let's do another example. Oh, what if I had this set? I call it Q, maybe, I don't know. I'm just, if I had 1, 2, 3, or sorry, 1, 3, 5. What if I did the odd numbers in Z110? Is that a ring, subring? No, why not? What breaks? It's not closed or under addition. If I add 1 + 1, I get 2, which is outside of my set, right? Anything else? What else breaks? What about the third one? It has no additive identity. There's no additive identity there. There's no zero element. And I think this example might make you a little bit careful or hesitant about like just looking for a 0 or just looking for 1, right? So you have to think about like, what is the function of the 0 element? What's the function of the identity element? And how can I find that in the table, right? So you want an element that has those properties, not necessarily that looks like a 0 or a 1. Now, I think you'll find for additive identity that they usually look like a 0. But multiplicative identity could look a little different. All right, so let's look at this another example. Move my iPad here. Okay, I'm gonna write down this thing. This is Z adjoin square root of 2. Is how you would say that in words. So I'll write that in words. Z adjoin square root of 2 is how you would say that. So we're doing Z adjoin square root of 2, and it's going to be A plus B square root of 2, such that A and B are in Z. So is that a subset, a subring of R? So you got to tick down the list and check them out. So for this one, I don't have a finite list, right? So I could do it in general by saying, like, say I have A plus B square root of 2, and then I have C plus D square root of 2. And I can prove it in general for these things and just kind of see, right? Do you have a feeling like it's going to be closed under addition? What's your feeling? What's your gut say? Yeah, seems like maybe closed under addition. Let's prove it. Well, maybe if this isn't proof, this is, well, unless we had a statement, then we can prove it anyway. Okay. So let's look at the first one. So if we had A plus B square root of 2 plus C plus D square root of 2. Now I need to use my ring identities or ring things to do this. So so I can use let's see. I can use associativity to drop these parentheses and move them. So I could do A plus B squared root of 2 plus C plus D squared root of 2, and that's associativity. And then I can switch those by commutativity of addition, right? So I get A plus C plus B squared root of 2 plus D squared root of 2. This is what I'm talking about. It can get a little tedious. Equals. And then I can do associativity and change and add those two and add those two, and then pull out use distributive property to pull the D out, the B plus D out, right? So anyway, so I get I use all the properties and I get A plus C plus B plus D squared root of 2. So we get something that looks like that, which is of the form A plus B squared root of 2. Right, so it's closed under addition. So we're going to try to be a little bit careful today to like make sure we're using all the properties of the ring, you know, and like go, okay, well, this is from associativity, this is from commutativity, this is from whatever. So it's kind of like, I mean, it's good to be careful and kind of slow down and pay attention to those things, because some things can slip under the radar and you think you can do something that you can't. So we're going to try to be a little careful today. I kind of hate it because it's like, oh, it's like, oh, it's so much. Okay, so let's look for multiplication. So if we do A plus B squared root of 2 multiplied by C plus D squared root of 2, what do we get? Okay, so we're going to have to use our properties. Okay. So I can use distributive property to distribute this to both of those, right? Okay. So I get A plus B squared root of 2 times C plus A plus B squared root of 2 times D squared root of 2. And then I can use distributive property to distribute those guys across those, right? So then I get and the distributive property we're using is because we are a subset of R, right? And R has those properties. So that's why we're able to do this. Okay, so I'm going to have AC plus B squared root of 2C plus AD squared root of 2 plus B squared root of 2 D squared root of 2. Okay. And so then I am in the reals, so I have commutativity of addition, commutativity of multiplication in the reals, right? So I can use that commutativity of multiplication, and I'm going to get AC, I'm going to use it a bunch of times, plus I'm going to get BC squared root of 2 plus AD squared root of 2 plus, and I just move those square root of 2's together, multiply them, I'm going to get BD times 4, right? And then I just want to gather all the things that don't have a square root of 2 and the things that do have a square root of 2, and I can do that by commutativity of addition and associativity.
Wouldn't it just be 2? It would just take.
Oh yeah, right. Yes. Thank you. Yep. Okay. All right. So then we're gonna do commutativity of addition to get. Well, I'll do commutativity a bunch of times to get it over here. Right? So I have AC plus BD times 2. Plus BC squared root of 2 plus AD squared root of 2, and then I can use associativity to gather these things together. I can use the distributive property backwards to take that square root of 2 out, right? So I'm going to get AC plus BD times 2 plus BC plus AD times square root of 2. So we're just using our ring properties of commutativity of addition, associativity, things like that, associativity of multiplication, over and over to get where we need to go. Okay, but all those are legal moves. Okay, how about the third thing? Do we have additive identity? And now that I pulled the rug out from under you, you're not sure. What do you think the additive identity will be?
Minus A minus B root 2.
So you're thinking of additive inverses.
Oh.
But that will be the additive inverse, yes. A and B should both equal 0. So 0, which is equal to 0 plus 0 square root of 2 is contained in Z adjoining 2. So it's of that form, right? And the fourth one, we have that if A plus B square root of 2 is in Z adjoining square root of 2, then we have negative A minus B or plus negative B square root of 2 also is in Z adjoining square root of 2. And maybe we should say that when we add those together, we get 0. So, and we can show that by using all of our things. So we add that to that, and we move things around using commutativity, and we do associativity and distributed property backwards, and blah, blah, blah. We get 0. Okay? All right. So is it a subring? Yeah, it's a subring. Okay, so let's do another theorem. So we're going to do theorem 3.3. So we're going to do today some properties of rings that were not in the definition, but things that we can prove using the properties of the definition that should be true, you know? So that's what we're going to do today. So here's theorem 3.3. So when you read that, you're going to be like, yeah, that should be true. And so we'll use the ring properties to prove it. Okay, so for any element in a ring R, the equation A plus X equals 0R has a unique solution. So I want you to look at that and compare that to what we know from the ring definition and tell me what this theorem is saying. Is this the same as the ring definition? One of the. Yeah, Colin?
That's saying, well, the ring definition just says that you can have an additive inverse. And this is saying that you can have the additive inverse for some element. There's only one.
There's only one additive inverse for each element. You see that? Because of the unique bit. Okay. Unique. So we're going to get a solution. We know we have a solution from the ring definition, but this is saying it has to be unique. So how do we prove something's unique? Assume there are two and show what has to happen, that they're equal to one another. Okay, so that's what we're going to do. I'm going to try to use the same letters as the book. Okay, so we know A plus X equals 0R has at least one solution. By axiom 5, is that what it was? Yeah, so a ring is just defined as a set that has multiplication, addition, and satisfies these axioms. So I guess we're calling it an axiom. Okay. In the ring definition. Okay, so we're going to assume that there are two. And there are kind of a couple of ways to proceed from here. So you could do a contradiction or do it by contradiction and assume that that U and V are not equal to one another, and then you'll get that they are equal to one another. But I kind of think there's no reason to do it by contradiction. You could, but I just like to go ahead and just say, assume that these are two solutions and then we'll just show that they're equal to one another, and that does the same thing. So, so I don't always usually do contradictions on uniqueness proofs, but some people like to do that. It's just a matter of taste, I think. Okay. So, all right, so how do we show this? Well, let's start with V. And then we're going to make a string of algebraic things here. And then we're going to get equals U. That's where we want to go. Okay. And we have to use our ring properties that we have, right? Okay. Well, so what could we say about V? What is V equal to? Definitely we know from the ring properties. Well, yeah, so we're going to say this from our ring properties. V is equal to 0R plus V. Why is that? That's because of the way that 0R works, right? So 0R is you can add it to any element of your ring and you just get that element back. So V is equal to 0R plus V. You might not have thought to go that way, but now I can say something about that 0R because I have this equation and I know, and it's going to be an opportunity to introduce V or introduce U into this thing, right? So what is 0R equal to that involves U? It's equal to A plus U, right? So now I get A plus U plus V. Okay. And maybe we'll put that in parentheses because I'm replacing 0R with that thing, right? Okay. So now what properties can I use? What do I want to get? I want to get U by itself, right? Yep, we can drop the parentheses. Okay, now what? Add parentheses back. Okay, wait. You did commutativity of addition, right? Yeah. So we did commutative addition, so we can maybe leave that in parentheses, and then I can do associativity to move it. So U plus A plus B, right? And what's A plus B equal to? 0R, right? So I get U plus 0R, which is equal to U. Okay. So we have this long string of things that says essentially V equals U. So I'm going to say, so I'll just write it in a sentence to summarize. So V equals U. Thus, what? So A plus X equals 0R has a unique solution. That's just a conclusion sentence. You could have stopped and not had that conclusion sentence. That's kind of nice to wrap it all up. Okay, so does this kind of give you a flavor of how these proofs go? You know, sometimes there's a little bit of ingenuity here, like going from V to 0R plus V. You might not have thought to do that, right? But those are kind of tricks that you'll start having in your tool belt, you know, that you can kind of think about. How can I get to where I need to go? I need to somehow introduce a U into this equation, right?
Creatively adding 0.
Yeah, creatively adding 0 or 1 or multiplying by 1. Yeah, so we do this all the time. Okay, so that's that theorem. Now let's keep going. Let's see how far I can get today. Okay, so here is this is going to be cancellation for addition, theorem 3.4. I'm trying to get to theorem 3.5, but I don't know if I'll get there. So maybe. Okay, so let's do theorem 3.4. So it says if A plus B equals A plus C in R, then B equals C. Okay. So how do we prove this?
Well, what would you do and if this were just numbers? Move A or subtract A from both sides, right? Can we subtract A from both sides in a ring? Do we know that there is an element, negative A, in that ring? Go back to our ring properties. What do we know? You should probably just keep this ring definition out. If you have that handout somewhere. Do we have a negative A in a ring? Benjamin says yes. By what axiom? Benjamin?
Fifth one.
The fifth one, I have a negative A, right? Yeah. So since R is a ring, by axiom 5, we have that negative A is in R for every A in R. And we know it's unique too by this other thing, right? So that unique bit will come into play in other proofs that we'll do. Okay, so we can add negative A to both sides. So I'll end up with negative A plus B equals negative A plus A plus C. And if you'll notice here, I'm being a little bit careful about adding it on the left side, you know, and we do have commutativity of addition, so it won't matter so much. But when we're talking about multiplying on both sides, you have to kind of be sure if you're in just a general ring, you don't know if it's commutative or not. Make sure you're always doing it on the same, like on the right side or on the left side, okay? And so it's just something you just have to kind of learn to be careful about. Okay, so if we do that, then we can do what? What's our next move gonna be? Yeah, or move the parentheses. We want to do a sensitivity. So we're gonna do a sensitivity. Negative A plus B equals negative A plus C. And what does negative A plus A equal to? It's 0R. And what's 0R plus B equal to? How would we put this? You will get to theorem 3.5. Okay, so theorem 3.5 is going to have a whole bunch of parts, and so I'm just going to turn y'all loose to prove as many of these parts as you can by yourselves, okay, or in groups. Okay, so here's theorem 3.5. And like I said, it's just a bunch of things that you feel like should be true. Okay, let me get a better marker. This marker's kind of. Okay, so for any, ooh, that's so much better. For any elements A and B of a ring R, we're going to have these bunch of properties. So we'll have A times 0R equals 0R equals 0R times 0. And in particular, 0R times 0R equals 0. Second one. A times minus B equals minus AB. And okay, and so what in the world is this even saying? Well, what do we mean by the negative of B? Well, this means the additive inverse of B. So if I multiply A by the additive inverse of B, what do I get? I get the additive inverse of AB, right? And so to show that, I'm gonna have to use this uniqueness bit, right? To show that if I could show that this guy is the additive inverse of AB, then I know it has to equal this because there's only one additive inverse of AB, right? So that's how that proof is gonna go. I know it may seem a little weird because you're like, well, duh, it should be that. And so, but we have to think about what are we saying here? So I'm just gonna put a little note here that this is the additive inverse of B, and then this is the additive inverse of AB, right? So that can kind of, that's what it's saying there. So, okay, third thing. Well, I mean, I remember proving things like this for the first time, and you prove things like, 1 plus 0R equals 1, and you're like, yeah, but in a ring, right, you have to use the properties to show that that works out in any ring, okay? So, anyway, all right, so what does this mean? Negative of negative A, okay. So what is this saying? This is saying the additive inverse of A is A. Okay. A lot of these deal with inverses. So the additive inverse of A plus B equals the additive inverse of A plus the additive inverse of, A minus B. There we go. The additive inverse of A minus B is the additive inverse of A plus B. Okay. So we're gonna get all this stuff. So, and then, oh shoot, 4 was a plus sign. Hang on, 5 has a minus sign. Now I've got you all screwed up. Okay. I got on the wrong line. Okay. Okay, so there are 4 and 5. They look very similar, but they are slightly different. And then 6 is the additive inverse of A multiplied by the additive inverse of B is equal to AB. So let me give you just a little bit of flavor. Like proving 2 through 6 is going to use the same sorts of strategies over and over and over. So I'm not going to go through the whole proof of that. The proof for number 1 is a little more similar to this kind of stuff, dealing with the 0R, right? And then the proof for 2 through 6 is going to be using that uniqueness bit, right, to show that this works out. So maybe I'll do 1 and 2 and let you do 3 on your own. Does that sound good? Okay, so I'll prove 1 and 2. That way you can kind of see the strategies of proof here. Okay, so for 1, I want to show that A plus 0R is equal to 0R. Okay, so we're going to go proof of 1. Okay, let me see if I can make sense of this. Okay. All right. So this is going to seem a little weird. So we're going to start with, and you won't be able to tell why I'm starting with this, but we're going to start with A times 0R plus A times 0R. And then we'll see where we can go from there. What does that give me? Well, I don't know. What did your gut tell you? What could I do with my operations here? Well, I can use distributive property backwards to get the A out, right? So I could do that. So I get A times 0R plus 0R. Well, what's that equal to? 0R, why? Because 0R plus anything is that thing, right? Right, so this is equal to A times 0R. And then what else do we know about 0R? Well, I can add it to anything and it doesn't change it, right? So that equals A times 0R plus 0R. And you might be like, who cares, right? But think about this, what is it saying? So what I've said here is that this side equals that side. So I said A times 0R plus A times 0R equals A times 0R plus 0R. Now I can use my cancellation of addition to get what? Okay, that may be a lot to look at, but I want to use this theorem 3-4, the cancellation of addition, to get what? Do you see it? What can I cancel on both sides?
A times 0R.
A times 0R, and that gives me what I want. Okay, so I can cancel that. So we'll have, so by theorem 3.4, we can cancel this and that bit, and I just get A times 0R equals 0R. Okay, so that was a little, those kinds of things are a little tricky because it's like, how did you know to start here? Right? You might not have thought of that on your own. Number 2. Oh gosh, now I'm almost out of time. Okay, so so let's say by definition and theorem 3.3, negative AB is the unique solution to AB plus X equals 0R. Agreed? Yeah. So any other solution must be equal to minus AB. Right? So what do I need to show? I need to show that this thing is a solution to that equation, and then I'll get that this thing equals minus AB. Okay. So let's plug that thing in for X and see if we can get 0R out of it. Okay, so I'll have AB plus that thing, A times minus B. And then I'm going to use my properties to get what I need to get. So what do? What's your gut say?
Undistributed.
Undistributed, yeah. Distributed property backwards. So I'm going to get A times B plus negative B. Then what? What's B plus negative B?
0R.
B plus its inverse, right? It's additive inverse. That's 0R. Then what? By
Part 1.
by part 1, I have that is equal to 0R, right? And so thus, since, and I'm writing out a lot of words here, but I want you to be able to follow this when you look back. Thus, since A times minus B is a solution, is also a solution to AB plus X equals 0R, we have that A times minus B equals minus C. All right, the rest of the proofs of these are very similar to part 2, right? So you're just going to be showing that these things are also the additive inverses of these elements. Okay. Good, that's all for today. There'll be more room stuff. So you should have it. You have plenty of information to start on your homework. So if you wanted to start on the homework for next week, you have the average wasn't low, yeah.
Okay.
But thank you for asking. Yeah, that's the kind of thing I would forget to announce. Right?
Thank you.